In this podcast, we'll discuss numerical solutions to differential equations. We'll only consider first-order ordinary differential equations in this podcast. In later podcasts, we'll deal with systems of differential equations or higher-order differential equations. We start with the differential equation dy dx, or y prime equals f of x and y, and we want to find y as a function of x. We have an initial condition, y of x0 is y naught. We want to find y of x. Often we cannot solve such equations analytically, and so we'll want to use the power of computers, and we'll develop methods to do that. Notice this is somewhat like integration, and so a lot of what we've learned in our studies of numerical integration should apply or should be similar in such a case. So if we integrate the left side, we have integral of y prime dx. Well, that's just equal to y. That should be the integral of the right-hand side. That's the integral of f of x and y dx, except that we don't know what y is as a function of x. Here are some important details, some basics about differential equations. We only want to solve problems if a solution exists and is unique. We don't want to solve a differential equation that has no solution. We don't want to attempt to do that and spend our time trying to search for a solution that doesn't exist. If f of x and y and f sub y of x and y are continuous near our initial point x naught y naught, there is a unique solution at and near x naught y naught. So that's an important aspect, that if your function f of x and y is defined and is nice in some way, that you could take the partial derivative of f with respect to y at the initial point, then there will be a unique solution at least nearby, for nearby values of x. We only want to deal with situations in which a small change in the initial conditions or a small error will not lead to very large errors in the numerical solution. That is, we want our method to be stable, and we want the differential equation to be stable, because if we make a small error on the computer, such as a round-off error, we don't want that to cause extremely large errors in our next step, because then the errors will just grow very quickly and not be reasonable. We won't be able to deal with those well. So if f of x and y and f sub y of x and y are not too large at near the initial point, then the differential equation we'll say is well conditioned. It's ill conditioned if a small change in the initial condition, if we changed x naught and y naught by just a tiny bit, and that would cause a large change in the solution, then it's not likely that our numerical method is going to do too well, because the differential equation will be very sensitive to the initial data that we put in, or to some small error that arises at some point. So we only want to solve differential equations that have a unique solution and that aren't too wildly behaved. Okay, here's the key concept. We only know the slope of the differential equation, the slope of our function, of our solution, at the start of the interval. We have an initial condition that gives us the x value and the y value at the beginning of the interval, and our differential equation, y prime of x naught at that point, is f of x naught y naught. That gives us the initial slope at x naught y naught. So all we have is the initial slope, but really we want to find out what's going on further away, not super close to our initial value. Well, since we want the value of x at the end of some interval, we really need to approximate the average slope of the function through the interval. We only have the slope at the left end at x naught, but let's say we want to find the function value at x naught plus h. We don't know the slope throughout the interval, but we want to develop methods that somehow will give us a reasonable approximation of the average slope. All the methods that we discussed are based on this concept, that you want to have an average slope, and all of them work to match Taylor series terms for the function y near the initial point x naught, right? If we have many terms of a Taylor series for a function, then we can get a good approximation for the function in some region around the point where the Taylor series is centered. So we're going to use concepts from Taylor series quite a bit here. The easiest method, the most elementary method that we use, is called Euler's method. right? We have the differential equation, y prime is f of xy, where y of x naught equals y naught. The true solution is capital Y. The approximate solution that we're going to use the computer to solve and to get is small y. So we know the slope at the beginning, and big Y and little y at the start are the same because we know the initial condition. Well, by Taylor series, big Y of x naught plus h is y of x naught plus h times y prime of x naught plus h squared over 2 factorial times y double prime somewhere on the interval between x naught and x naught plus h. If we truncate this Taylor series after the h term, we leave out the h squared term, we get y of x naught plus h is approximately y of x naught plus h times y prime of x naught. And that gives us Euler's method. That is how we define Euler's method, that our approximate value of y at x naught plus h will be the initial value of y plus h times the slope at x naught, y naught. So that's how we moved one step along, and then we would use that small y value at x naught plus h to march along again. We'd get y of x naught plus 2h is y at x naught plus h times f of x naught plus h, little y of x naught plus h. Okay, here's an example of using Euler's method, right? This is the method, y of x naught plus h is y of x naught plus h times f of x naught, y naught, which in general at the nth step would become yn plus 1 equals yn plus h f of x and yn, where yn is y of x naught plus nh. So suppose we have the differential equation, y prime equals y over x squared plus y. It's not so easy to solve that differential equation, not so obvious how you do it analytically. And suppose we have the initial condition, y naught equals 1. We would just plug that information in. So at the start, we'd have x naught equals 0, y equals 1. We plug that into here. Y prime is 1 over 0 plus 1, so y prime is 1. And suppose we use a step size of h is 0.1. So then at x equal 0.1, we would get y at 0.1 is equal to y at the initial location, which was 1, plus h, which is 0.1, times f of 0, 1. F of 0, 1 we said was 1. So you get 1 plus 0.1 is 1.1. And then we could plug in 0.1, 1.1, and get a new slope. And we'd get y2 is equal to y1, which was 1.1, plus 0.1 times the slope at 0.1, comma 1.1. And if we plug that in, we'd get this value over here, 1.1 over 1.11. And we'd plug that in, and so we'd get that our approximation for y at x equal 0.2 is 1.199. So let's discuss some basic error analysis. Our approximation is y of x naught plus h is equal to y of x naught plus h times f of x naught, y naught. The exact solution, capital Y, well, that's our Taylor series where we have through the second order term, and we've taken the y double prime somewhere in the middle. And this last term, the h squared term, that's called the truncation error. That's, we've cut off our numerical method. We've cut it off after the h term, and so this is what we've left out. We've left out the h squared over 2 factorial y double prime piece. So simple analysis tells us, well, that our error after one step is going to be roughly h squared over 2 factorial times y double prime. Okay, now if it takes us n steps to go from x equal a to x equal b, so our step size, if we take n steps, h will be b minus a over n, or switching n and h, you get n is equal to b minus a over h, and the error is going to be approximately h squared over 2 factorial times y double prime somewhere at each step times the number of steps, which is n. We plug in b minus a over h for n. H squared and h cancel, and so we just get h over 2 factorial y double prime times b minus a. In other words, the error of Euler's method in going from x equal a to x equal b will be something like h times other stuff. In other words, the method is order h. So that means if we have the time step, we'd half the error. Like if we have our h's, then our error on going from A to B, we could expect to become about half the error. So it appears that the error grows linearly with the interval length. One can perform a more careful error analysis. And here's a slide that details all of that, where we take y at xn plus 1 or xn plus h, and we write out the Taylor series through the quadratic term. And our method, our Euler's method, we write out. We can subtract. We can do some algebra and some calculus on there. And what we can find is the error at the new step is equal to some mess times the error at the old step. Y at xn minus y, and capital Y minus little y is the error at step n. And so the new error is 1 plus something times the old error plus an h squared over 2 factorial term. One can do further analysis with it and find that the error after n terms is related to the initial error. And the initial error we hope is going to be 0, but it would be times an e to the b minus a times a number that's related to how fast f changes with respect to y, plus another piece that's also exponential, e to the b minus a. It's related to the second derivative of the solution, which we don't really know. So the solution, the error, is more complicated than just simply order h, but it still is an order h error. It's just h times something a little more messy than what we said before. So the error in Euler's method is order h. The error grows exponentially with the interval length, but the order h still holds. There's an example that one can go through carefully if you want to in the slides for the error and analyzing the error according to this formula that we had over here. And one can find out how the error grows at its order h times e to the length of the interval. Here's a moment of culture. We have a car parked in a certain spot. Can you figure out what number spot this car is parked in? We have spot 16, 6, 68, 88, our car, and 98. What number spot is in here? Take a moment to think about that. And here's the answer. We just turn it upside down. We see the spots are really 86, blank, 88, 89, 90, and 91.